So now we're going to continue on with graphing exponential functions. So this is going to be part 2 of section 4.1. Let me just remind you what we did last time. We talked about some of their properties. Okay, we're going to be using the fact that it's going to be a nice continuous function having domain negative infinity to infinity. We have to keep an eye on the range. The range for a default exponential function will always be 0 to infinity, but transformations will change that potentially. Okay, all rational functions of the form b to the x, they pass through these 3 points. When you plug -1 in, you get the reciprocal of the base. When you plug 0 in, you get just 1, because anything raised to the first power, sorry, 0th power, except for 0 is 1. And if you plug 1 in, the base to the first power is just 1. The horizontal asymptote for a rational function, sorry, an exponential function, is always going to be 0 unless, again, some particular transformation is applied, especially vertical transformations when you do a vertical reflection over the x-axis or a vertical shift. That will affect the range and the horizontal asymptote. So we're going to be using these properties and these 3 points here to graph these functions that are on your handout. So let's look at the ones that are on your handout. And I'll try to go through these relatively quickly. Again, you can always pause, rewind, ask questions in discussion. So use that to your advantage. So the first one we have here, this is just like we did before, it's similar. Before we graph 2 to the x, now we're going to graph 3 to the x. So the points we're going to have, the points we're going to use are going to be -1, the reciprocal of the base. So here the base is 3. So the reciprocal of the base is 1/3. When we plug in 0, we'll get 1. When we plug in 1, we just get the base. So let's plot those points. Oh, so the general behavior, since the base is larger than 1, we know the graph is going to look something like this. Okay. Using all of that, we can get a quick and easy sketch of the graph of this exponential function. On the handout, you do have x and y axes, so I'll just do my best to approximate what you have. You'll have more range for your x and y values there. So when we plugged in -1, let me zoom in a little bit maybe. When you plug in -1, you got 1/3, which will be about right there. When we plug in 0, we get 1, and we plug in 1, we get 3. So you can see the points are agreeing with this general behavior. So you just want to connect them in the appropriate way. Remember, this function has a horizontal asymptote at y equals 0. And this will be to the left, so as x goes to -infinity. So we can see that happening here. I'm going to have to get really close to the x-axis here eventually, to the left. Then you just connect those points in a nice smooth manner. And that will be the graph of f of x is equal to 3 to the x. Again, its domain is -infinity to infinity, and its range is 0 to infinity. So that's the first one. Let's look at the second one. Here we're looking at f of x is equal to e to the x. Remember the number e I talked about in the first video? We're going to pretend that e is basically the same number as 2.7, just for graphing purposes. So we're going to picture it to a number that's close to but less than 3. So the points of this function will be -1, the reciprocal of the base, 1 over e, 0, 1, and 1e. So approximating these, I'm going to say this is approximately -1 comma 1/3. It's going to be larger than 1/3 because you're dividing by something that's about 2.7, but at least for graphing purposes, we're just going to approximate it to be about 1/3. As a result, the graph is going to look pretty similar to the one we just did. Not much difference because we're, again, approximating. So this one, there's no need to approximate. This one, I'll say it's it's approximately 1 comma 2.7. Again, because the base is larger than 1, since the base behavior, since the base is larger than 1, it's about 2.7, we're going to have the general behavior be the same as last time. The next example will not be like that. So there's a horizontal asymptote, once again, y equals 0, and that's as x goes to -infinity. So let's plot these points just like before. So at -1, we're at 1 over e. So 1 over e is going to be right around where 1/3 is. When we plug in 0, we get 1. And when we plug in 1, we get e. E is just short of 3. Again, 2.7-ish. So we'll get that point. So these 3 points are going to connect the same way we did in the previous example. You can see there's not much difference at all. And we're going to see the same situation whenever the base is larger than 1. Right? So that's number 2. Number 3 here is a little bit different. We have f of x is equal to 1/3 to the x. In the previous video, we did graph 2 to the x and 1/2 to the x. So in the first example here, we graphed 3 to the x. Let me scroll up to that. In the first example, we graphed 3 to the x. It's going to have a similar kind of behavior relationship between 2 to the x and 1/2 to the x. So 3 to the x and 1/3 to the x have that similar relationship with the reciprocal. So the points will be -1, 1 over the base. 1 over the base means take the reciprocal of the base. The reciprocal of 1/3 is 3. When we plug 0 in, we'll get 1. When we plug 1 in, we get whatever the base is, which is 1/3. The behavior, since the base is between 0 and 1, that means the behavior is going to be a reflection over the y-axis, so it'll look something like that. And when you plot the points, you can see the points agreeing with that behavior. And this will have a horizontal asymptote of y equals 0, but in this case, it'll be as x goes to +infinity rather than -infinity. So let's plot our points. So -1, +3, 0, 1, and 1, 1/3. So we can see the points having that behavior, right? They're sloping down to the right versus sloping up to the right, like in the first 2 examples. So this graph looks something like this, pretty similar to the 1/2 to the x function. So that's 1/3 to the x. It's number 3. Number 4, we have f of x is equal to 0.25 to the power x. Since the base is also between 0 and 1, it'll look pretty similar to number 3. So the points here that we're going to use is -1, 1 over the base. Now, it might be helpful if you know how to convert, and you should know how to convert fraction or decimals to fractions. This is the same as 1/4 to the x, right? A quarter, 0.25, is the same as 1/4. So noticing that, when you divide 1 by 0.25, you will get 4. When you plug in 0, you'll get 1. Now when you plug in 1, you'll get the base, which is 0.25 or 1/4 if you prefer to use the fraction version of that. So the behavior, what does it look like? Well, just like the previous one, since the base is between 0 and 1, it'll look something like that. And the horizontal asymptote will be y equals 0 as x goes to positive infinity. So knowing that, we can sketch this graph pretty quickly. So we have -1, 4. We have 0, 1. And we have 1, 1/4, but I'll write it as 0.25, right about there. So it looks like that. Now there is a difference. Again, just comparing these, we can see that the y values are smaller the closer you are to 0 here than the 1/4 to the x to the left of the y-axis. So 4 to the x, or 1/4 to the x, will increase faster as x goes to negative infinity than 1/3 to the x will, but their general shape is still kind of the same. So that does it for the 3 basic examples. Let me just go through it one more time. So to the graph of 3 to the x, we saw it sloped upward. E to the x also sloped upward, again, because the bases were larger than 1. The graphs is 1/3 to the x and 0.25 to the x. They decreased as x got bigger, right? They sloped down towards the x-axis. But remember, it never touches it either. So those are the first 4 basic examples. Now we're going to talk about transformations. So regarding transformations, it's been a while since we've done them in section 2.5, but I think we spent a lot of time with it. Hopefully some of this seems familiar to you. There's one minor difference in the aesthetics of how the transformations look. And so for transformations, of exponential functions, there's 2 things you have to remember. So remember the horizontal transformations, we had the shifts, the reflections, the stretches or shrinks, and for vertical, we had an analog of those as well. So for horizontal transformations, remember, horizontal transformations happen to the input, right? So there's a modification to the input. And I'm going to quickly go through them again, just to remind you, but so something's happening to x inside the function, but for exponential functions, inside the function, where does the input go for an exponential function? So inside the function means in the exponent. So if there's a modification, so if it's not just x as your exponent, if it's 2x or x plus 3 or negative x that is in your exponent, that means that there's a horizontal transformation happening. So for example, the following 3 functions, call them g of x. Let's say we had 2 to the x plus 1, or g of x is equal to the to e to the negative x, or g of x is equal to e, or different number, 5 to the 2x plus 7, we can see that, I mean, comparing them to just 2 to the x, e to the x, 5 to the x, the difference is what's happening in the exponent. That is the modification that's happening to the input. So all of these three examples will have horizontal transformations. So unlike this with the square root function, we could obviously see what's inside the square root, or like the square function or the cube function, whatever it may be. With polynomial and algebraic functions, it was more obvious what was inside the function. So we have to kind of remember that inside the function for an exponential means in the exponent. Vertical transformations of an exponential function, not too different from what we've already seen. Remember that this is a modification of the function itself. So we're changing what's happening to the actual function. Are we multiplying the function by something? Are we do we have a minus sign in front of the function? So here's some examples that are vertical transformations. Let's say I had g of x is equal to 4 times 3 to the x. That means whatever the output of 3 to the x is, I'll end up multiplying them by 4. So this one ends up being a vertical stretch. G of x is equal to, say, e to the x minus 2. Here I'm subtracting 2 from the function e to the x. So that's a vertical transformation. And of course, you can have combinations of both, but I don't want to get them all too confused right now. We'll talk about multiple transformations in a little bit. So another example would be, say, g of x is equal to negative 5 to the x. Here, we're taking the function 5 to the x, and we're negating its output. So we're changing the sign of the y values, if you will. So these are all examples of strictly vertical transformations. So let's step through them, and just a quick review before we get to the examples on the handout. Let's look at the list and order of transformations. Nothing's changed from before. We're still being consistent. It's just now that we're dealing with a different function, things may look a little bit different. Remember the first transformation we always did? Always first. Okay, that is a horizontal shift. So let's look at the horizontal shift. That means we're going to move the graph left or right from the original parent graph or base graph. So horizontal shift, we'll say the graph. So for all of these, we're going to assume that c is some positive real number. So for all the transformations, we're going to assume the letter c represents a positive real number. So horizontal shift, so we're going to say the graph of ... g of x is equal to b to the x plus c, right, is the graph, maybe just to save a little bit of writing. So we're going to let c be greater than 0, and we're going to let f of x be the parent function of b to the x. So I'm going to assume f of x is always b to the x. So the graph of g of x is equal to b to the x plus some positive number is the graph of f of x shifted left c units. Okay, so if we're adding a positive number to the input inside the function or in the exponent, then we're going to shift the graph to the left. If we're subtracting then that will be the graph of f of x shifted right c units. So that's what a horizontal shift will look like. And we do have the first example on the next page is a horizontal shift of what we've already graphed prior. The second transformation we looked at was a horizontal stretch or shrink. That means we're either going to be yanking on the graph and pulling it out sideways from both sides, or pushing on the graph from both left and right to squish it in. So that's what a horizontal stretch or shrink is. So the graph of g of x is equal to b to the x, or c times x, is a horizontal stretch or shrink. So it really depends on the size of c. If 0 is less than c is less than 1, which means if c is a number that's multiplying x like a half between 0 and 1, we're going to have a horizontal stretch. If c is greater than 1, then we have a horizontal shrink. And no matter what, if it's a horizontal stretch or a horizontal shrink, it really doesn't matter. To get your new x coordinates, you're just going to divide the x coordinates by c. So you're going to divide the x coordinates by c. Whatever they are for the base function, you keep the y values the same, just divide the x coordinates by whatever that number c is, and you will get your new points for your graph. The next transformation was a horizontal reflection. Okay, horizontal reflection, or in other words, a y-axis reflection. That occurs when you have a negative sign in front of your input. So the graph of g of x is equal to b to the negative x is the graph of f of x reflected over the y-axis. So you're just going to negate the x value. So the actual process is you negate or change the sign of the x coordinates. You keep the y coordinates the same. So that's it for the horizontal transformations. So now we're going to look at the vertical ones in kind of a reverse order. So let's look at vertical reflection. That means you're flipping the graph over the x-axis. So we'll also refer to this as an x-axis reflection. So we say the graph of g of x. So here, the minus sign is not in front of the x anymore. So for these first three transformations, look what we're doing in the exponent. We're either adding or subtracting something from x, we're multiplying x by some fixed constant, or we are negating the x. Okay, so for vertical transformations, remember they're happening to the function. So a vertical reflection will look like this. This is a minus sign in front of the function. So you figure out what b to the x is first, then that minus sign applies second. Note that this is not the same. So negative b to the x and negative b to the x are very different. They mean completely different things. So that minus sign applies after you evaluate b to the x in this case. Here you raise negative b to whatever the power of x is, so be careful there. So the graph of negative b to the x is the graph of f reflected over the x-axis. That means we're going to negate the y-coordinates, keeping the x-coordinates the same. So for example, just really quick, if the point 2, 7 was a point on the graph of the original function, we would keep the x-coordinate the same and negate only the y-coordinate. Okay, going in order again, we can look at the vertical, stretch or shrink. So for the horizontal stretch and shrink, remember we were multiplying the input by some number c, some positive number c. Here we're going to be multiplying the function by some number c. So we say the graph of g of x is equal to c times b to the x is a vertical stretch or shrink. Of the graph of f of x. So how do you know which is which? Well, this is opposite of what we saw with the horizontal, okay? So if c is between 0 and 1, then there's going to be a vertical shrink. If c is larger than 1, we get a vertical stretch. So in this case, what would you do with those coordinates? Those, at minimum 3 points. I gave you 3 points. That should be enough to get the final graph, a good sketch of it. So in this case, you multiply the y-coordinates by c. Notice with the horizontal stretch and shrink, we divided the x-coordinates by c. But for a vertical stretch or shrink, we multiply the y-coordinates. So we have discussed this prior, but it was a while ago. The horizontal stuff happens kind of opposite to your intuition. If you're adding a positive number to x, it actually moves to the left, in the negative direction. If you're multiplying by a number larger than 1, your x-coordinates get shrunken down, they get smaller. So the horizontal stuff is kind of opposite of what you might originally think, but the vertical transformations, they happen the way you think they should. So if you're multiplying the function by something, it's going to get bigger if it's larger than 1, if you're multiplying by something larger than 1. Finally, we have one more transformation. That is the vertical shift. So let me remind you, going back to the original, the first transformation, you must do horizontal shifts first. All of the other stuff, the stretching, shrinking, dilating, reflecting, that can be done in any order. I would think it's good to go in some logical order, right? So looking at them in kind of this way, an inside-out approach, then just applying things as you see them. But numbers 2 through 5, you can do in any order, but the vertical shift must be last. So the horizontal shift is first, the vertical shift is last. Those are the most important things to keep straight. Although knowing the order that I gave you, I feel like it's intuitive. So I personally would follow this ordering. Anything else? There are other there are different ways to teach the subject matter. So if you look online and they're giving you an ordering that's different from this, do not pay attention to it because they teach it differently. They'll say, do this in this order, but when they say a vertical flip or a vertical reflection, it may not be the same thing as an x-axis reflection. So just be careful if you're using other resources. I think you should be checking out other resources, why not? But just be careful, make sure they're following the same or similar approach as I am. So for a vertical shift, that's moving the graph up or down, just adding or subtracting from the y values. So the graph of ... g of x is equal to x plus c, or sorry, b to the x plus c. So here you're literally adding a number, a positive number, to the output of the original function. So that'll move it up c units. So this is a vertical shift up c units. So you would add c to your y values. And for g of x is equal to b to the x minus c, that's a vertical shift down c units. So even though, again, it looks a little bit different, especially for the horizontal transformations than what we did in 2.5, the concept is really identical. It just depends on how you write the function. In fact, some people, for e to the x, it's common to write the function exp of x. So these are really the same function. So if you were looking at exp of x plus 2, using the 2.5, you would look, 2.5 idea, you look inside the function, you'd say, oh, I'm adding 2 to the value of x. Well, that's going to be the same thing as e to the x plus 2. So again, we're looking at the exponent to see what is actually inside the function. So now we're going to look at the actual handout examples, and that will be the end of 4.1. The compound interest application problems, if we have time in the future, I will cover them, but at the moment, we are not going to cover that. We're going to move on to 4.2. So the first example on your handout is this function. So let's go over these examples from your handout. Number 1 here, we're asked to graph the function f of x is equal to 3 to the x minus 1. To identify the parent, or what I'm calling here the base function, so I might just change it to parent function. So I call this base function on the handout, but it's really the parent function. I changed my vocabulary because we talk about bases of exponential functions, and then the base function, it could be a little confusing. But the parent function here, to identify the parent function of any exponential function, just look at the base. The base is 3. So the parent function is just 3 to the power x. And that's going to hold true for every single exponential function you're doing via transformations. You just look at the base, and whatever the base is, that to the power of the variable is your parent function, right? So that's the parent function. And the points, your initial points for your parent function, we did this previous, right? We did this in the previous, no, we did this right above. When we graphed these functions, we already know this graph. Right, we already did this. So we're going to start with the initial points. Then we have to identify the transformations. So the transformations what's different between the function that we're asked to graph and our parent function? Well, the only difference is in the exponent. That means you can narrow it down to one of those 3 horizontal transformations. So what is happening to x? Well, we're either adding or subtracting something from x, multiplying some positive number to x, or maybe there's a negative sign in front. Okay, in this case, we're subtracting 1. And if you go back above, I'll scroll up, go up here, the very first transformation, right here, the graph of b to the x minus some positive number is the graph of the original function shifted right, that number of units. So in this problem, we're subtracting 1. So the transformation here, there's only one transformation. That's going to be a horizontal shift right, 1 unit. Okay, so what we're going to do is graph the base function again pretty quickly. So let's do that pretty quickly. So let's graph that parent function, that capital F of x. Just a rough sketch. Since you have x, y axes, you can do a better job than me as far as neatness. But we basically were in this situation, -1 1/3, 0 1, and 1 3. Remember that had a horizontal asymptote of y equals 0 to the left as x went to -infinity. Now for my transformation, I'm basically going to shift each of these 3 points right 1 unit. So I'm going to shift the point at -1 1/3 to 0 1/3. I'm going to shift the point at 0 1 to 1 1, and shift the point at 1 3 to 2 3. It should be roughly parallel, and it should look something like that. Remember I showed you the website desmos.com? Feel free to use that to check any of your graphs to make sure you're doing the problems correctly. So that's the first example, just a horizontal shift. Now we're going to look at the second example, number 2. Number 2 is f of x is equal to 2e to the x. So what is the parent function here? I guess you should be a little bit careful. You might be tempted to think it's 2e, but here, remember PEMDAS, right? So exponentiation gets done before multiplication. So really it's 2 times the function e to the x. So this is our parent function, e to the x. Which we already graphed. And in fact, each of these we've already graphed, the base functions at least, we've done previously. So the initial points, remember they were -1, 1 over e, 0, 1, and 1e. But what transformations are we looking at? Well, looking at the exponent, nothing's changed, right? It's just an x. So that means that there's no horizontal transformations. But it is different from the base function. So what kind of transformation is it? Well, we see this 2 out front. And if you refer to the previous list of transformations, when you're multiplying your function by a number that's larger than 1, that's a vertical stretch. And there's only one transformation, right? That's the only difference between the function we're asked to graph and our parent function here. So we only have a vertical stretch, which means we're just multiplying our y values by 2. Even if it was a vertical shrink, if that had been a 1/2 outside the e to the x, we would still multiply the y values by 2. So let's give this a go. This one actually might be a little tight, so let me draw it a little bit more out in the open here. Because we're multiplying the y values by 2, I know they're going to get taller than my previous 2 graphs. So remember, E is about 2.7, okay? 2.7, which means when I have to double that, and I will have to double that, I'm going to get that 2E is about 5.4, somewhere between 5.4 and 5.5. So we're going to need to do that. So let's plot our initial points. 1 over E, remember that's kind of around 1/3. So we'll get this point, 0, 1, and 1E. E is a little bit short of 3. So right there. So that's our initial parent graph. So now what I'm going to do is multiply the y values by 2. So here, 1 over E, if I multiply 1 over E, which again, I'm assuming is 1/3. So if I multiply 2 times 1 over E, that'll be approximately, again, not extremely close, but close enough for our purposes, that'll be about 2/3. We just want to know the vicinity in which to plot the point. So this point here at -1, 1 over E, it's going to move up to about 2/3, twice how high it was before. This point here, if I multiply its y-coordinate by 2, it's going to move up to 2. And this point here, E, if I multiply it by 2, it'll move up to about, so here's about 2E. It'll move up to here. So we've literally just stretched the graph out. It'll look something like this. We're just kind of yanking up on it. And that is a rough sketch of f of x is equal to 2 times e to the x. All right, so let's move on to example 3. Example 3 is, so the next two functions have 2 transformations in them. So we just have to make sure we're doing stuff in the right order. So for f of x is equal to 1/3 to the x plus 2 minus 3. So the base function, again, what we want to do is just look at the base. What is the original base here? That's 1/3. So my parent function, or base function, which that's what I wrote on the handout, that's just 1/3 to the x, which again we have graphed earlier. So my initial points were -1, 3, 0, 1, and 1, 1/3. If you don't remember how I got these, just look back earlier in the video when I graphed 1/3 to the x. So what transformations are we talking about here? Well, there's 2. Remember, the first transformation you always look for is a horizontal shift. Is there a horizontal shift? Meaning, for exponential functions, is there something being added to or subtracted from x in the exponent? So in this case, if we look at the exponent, again, that's where all the horizontal transformations happen. What's happening to the input? We can see that we're adding 2 to the input. that means there's a horizontal shift. And because we're adding a positive number rather than subtracting a positive number, this means there's a horizontal shift to the left by 2 units. Is there anything else happening to x? Well, nope. Okay, there's no number in front of x multiplying x. There's no sign in front of x. That means that that is the only horizontal. There's no minus sign in front of x. So there's no horizontal transformations besides this one. Now let's jump to outside the function. What is happening to the 1/3 exponential function, the exponential function of base 1/3? Well, there's nothing out front. There's no number multiplying that b to the x. There's no minus sign in front. So there's no vertical stretch or shrink, as we saw in number 2. There's a vertical stretch in number 2. There's no minus sign in front, so there's no vertical reflection. So there's no x-axis reflection. But I do have this -3. Here we are subtracting the number 3 from the function itself, and that is a vertical shift down 3. So those are the only 2 transformations of our base function. So let's start with our base function, which I'll graph in the ordinary color here. So now I'm shifting it down, right? So I'm going to go back. I just realized I forgot the horizontal asymptote, domain, and range. I'll go back and do those after I finish graphing. So I'm going to start with my initial points here, which look like this. All right. So that's my that's my parent graph. So the first thing I'm going to do is I'm going to do this horizontal shift. I'm going to move those points left 2 units. So each of those points I'm going to be subtracting 2 from. So this point, maybe I'll have to go a little bit further here down to -3. So this point here, if I shift it left 2 units, it's going to go to -1. I'm not changing the y coordinate at all. Here, I'm at 0, x equals 0. If I shift it left 2 units, it's going to go to -2. And if I take this point here, if I shift that left 2 units, at x equals -3. So it's basically you're picking up the graph and just moving it over 2 units and then letting it go, dropping it down. So that is the first transformation. The second transformation is I'm going to move each of these 3 red points down 3 units. So this point, which was at 1/3, if I move it down 3 units, I'll end up at 2 2/3, or just above 3. I'm not going to worry about the exact number there, but so it'll end up at -2 2/3 because you're moving it down 3 units. So it was just above 0, now it's just above 3. The second point here from the right, if I move that down 2 units, it was at 1. Now it's going to be at -2. Finally, this point here, this one was at 3. If I move that down 3 units, it'll be at -3. So that red graph there, just imagine picking it up and just moving it down 3 units. Now, before I sketch the graph, this is important. Remember, each of these had the horizontal asymptote of y equals 0 before we applied any transformations. When you would do a vertical shift, the horizontal asymptote is going to move with the points. So originally, my horizontal asymptote was right here at the x-axis. I have to move that down with the points. So I'm going to have a new horizontal asymptote here at 3. So before, when I was approaching the x-axis, by moving it down 3 units, now I'm going to approach x is equal to -3. So I'm going to connect the points in the same way. Just make sure you don't cross that horizontal asymptote. You get really close to it, but you just never cross it. I don't know why OneNote keeps deleting my words there, but that's supposed to be horizontal. Shift. Okay, so that's the third example. Remember, vertical shifts will affect your horizontal asymptote. Originally y equals 0, but that can change. So we have one more example to go, number 4 here. And this is f of x is equal to negative 0.25 to the power x plus 3. So let's look at the parent function first. We've already graphed that. Just looking at the base, and be careful that minus sign is not part of the base. -3 to the x is not the same as -3 to the x. I mentioned that before, but it's very important that you understand that. So that minus sign is not part of the base at all. This exponentiation takes precedence before that minus sign is even considered. So the parent or base function is capital F of x is equal to 0.25 to the x, which remember, its initial points. They were -1, 4, 0, 1, and 1, 1/4. You could use the fraction version if you prefer, just like we did for this function here. 0.25 is exactly the same as 1/4. So what transformations are we looking at here? Let's see, so our transformations. Well, let's compare this to the parent function. What's different between this expression and this expression? Looking at the exponent, is there any difference between them? Just the exponent? No, they're both just x. Nothing is happening to x in this function here. That means that there's no horizontal transformations. Any other transformations that will show up have to be vertical. So since there's no horizontal transformations, let's move on to the vertical ones. Is there a positive constant multiplying the front of this base? The base being 0.25. There's not. For example, it's not 3 times 0.25 to the x, right? There's no number, positive number in front multiplying our expression. So that means there's no vertical stretch or shrink. But we do have this minus sign. So that minus sign in front of the exponential function means that there's a vertical reflection. So there's a vertical, or in other words, x-axis reflection. So whatever my original coordinates were, the first thing I'm going to do is I'm going to negate the y values of those coordinates, get my new coordinates. So we negate the y values. Okay, so that's what that minus sign in front means. Okay, what about this +3? Okay, that +3, just like we saw in the previous example, there was a -3 in the previous example. This +3 is also a vertical shift. But instead of moving down, because we're adding to the input, adding a positive number to the output, we're adding a +3 to the output. So there's going to be a vertical shift up 3 units. So with all that in mind, we are ready to graph this function. So we're going to start again Since we're moving up 3 units, I'm going to leave a little bit more space at the top. Oh, and remember, since there's a vertical shift, that's also going to change the horizontal asymptote. All right, so it's not going to be y = 0 anymore. So let's see, originally, the parent graph, our points went up to y = 4. Since I'm adding 3 to the outputs, I know ahead of time that I'm going to have to go up to 7. Which, unfortunately, on the graph paper I provided you, you won't be able to go that far. Just do your best. You can extend beyond the axes that I gave you on your graph paper. So let's look at the parent graph. The parent graph will be going through these points, -1, 4, 0, 1, and 1, 1/4. So a little bit steeper than the 3 to the x graph or 1/3 to the x graph. Okay, that is our parent function. I can do a better job than that. Maybe not that much better, but. So that's our parent graph. Now let's apply the first transformation. And if you feel comfortable, you might be able to do multiple transformations at once. Like if there's only 2 transformations, you could potentially do them consecutively for each point. I'm just going through kind of the most general approach to this. I want to do each thing separately. So the vertical or x-axis reflection, what that's going to do is it's going to flip the graph over. So I guess I do need some more negative territory here. So that'll be, well, I guess I won't have to go up to 7 then, will I? Oops, whatever. So if I were to flip the parent graph over the x-axis, then that's going to negate the y value. So this point here, I was at 1/4. Now it's going to be at -1/4. This point here was at 1. Now it's going to be a -1. This point here is at 4. It's going to now be at -4. So we're literally just flipping that over the x-axis. So that's the first transformation. The second transformation is to look at each of those red points, and I'm going to move them up 3, right? Vertical shift up 3. So this point was at -1/4. If I move it up 3, it'll go to 2 3/4, which will be about right there. Now, you don't even necessarily have to figure that out. You should be able to at this level. But all I'm doing is I'm hopping 1 unit 3 times, and that gives me where my new point is. This point here at -1, if I move it up 3, I'll end up at 2. And this point down here at -4, if I move it up 3, I'll be at -1. Now, before you sketch your final graph, just like we saw in the previous example, since there was a vertical shift that changes your horizontal asymptote, the horizontal asymptote moves with the points. So it used to be here at y = 0. When we flipped it over, the x-axis, when we did that x-axis reflection, the horizontal asymptote did not move, right? The graph did, but we're still approaching the same horizontal asymptote. But now, since the vertical shift moved everything up 3, I'm going to draw that vertical asymptote first. Sorry, I keep saying vertical, horizontal asymptote first. And then I'm going to approach the horizontal asymptote the same way that I had the red graph approach the x-axis. So it'll look something like this, if you don't miss your points. Something like that. So this is f of x. A very rough sketch of what f of x is equal to -0.25 to the x plus 3 looks like. Again, use Desmos. Check your answers for these. You can try them out first, and then check your answer, then compare them with what I did here. So we're essentially done. Let me just go back because I forgot to answer. If you look at the handout, I asked you for the horizontal asymptote, the domain, and range for each. So let's start with number 4 here. Let's give the horizontal, based on the graph, horizontal asymptote, the domain of f. Let's use the notation we use in class, the domain of f, and the range of f. The horizontal asymptote, we saw that by flipping the graph over first, and then we had to move it up 3, the horizontal asymptote became y is equal to 3. And that changes the range too. The domain for an exponential function will never change, even if you apply transformations like these. So the domain of f is negative infinity to infinity. You can plug any number you want to into an exponential function. The range of f, though, that has definitely changed. Again, just looking at the blue graph, we see that that down arrow on the left-hand side says that this goes down forever and ever and ever. There's no limit to how negative that graph will become as x goes to the left. To the right, though, we see that the graph will never go above 3, and in fact, it'll never reach 3 either. Remember how the exponential graph, the base parent function, could not touch the x-axis? Well, now we still cannot touch that horizontal asymptote. A shift and a reflection don't change those facts. So the range of f here, so it can go as low as it wants down to negative infinity, so it's going to start at negative infinity. But the highest it gets is y is equal to 3, but doesn't even get there. So we have to exclude that. So in interval notation, that would be the range. Everything is negative, as you can imagine, all the way up to 3, but not including 3. So that's it for the fourth function. For the third function, let's just look at its graph. There you go. Let's look at its horizontal asymptote, its domain, and its range. Here we also saw, because there was a vertical shift, the horizontal asymptote did change. Originally, it was at x equals 0, but because of the vertical shift, we moved it down 3 units with the points, and the horizontal asymptote is now down here. Right? So the horizontal asymptote here is y is equal to negative 3. And that's as x approaches positive infinity. The domain, again, for any exponential function, even with these types of transformations, negative infinity to infinity. Because of the vertical shift, the range did change. So remember, the range for a parent function is always 0 to infinity, but because the graph got moved down to negative 3, okay, the range changed also. So if we look at the y values, okay, we get as low as negative 3 and as high as we want. So the range will be from negative 3 to infinity, but remember, it's not going to meet its horizontal asymptote, so it won't be equal to negative 3 ever. So the range of f will be negative 3 to infinity. Finally, let's just look at, oh, this is number 2, it's not finally. Number 2, so let's look at the horizontal asymptote, the domain of f, and the range of f. Because there was no vertical shift, the horizontal asymptote did not change. It's still y equals 0. It's going to approach it maybe twice as slow or somewhere thereabouts, but it's still going to approach the x-axis as x goes to negative infinity. The domain, no change there, everything. And because, again, there's no vertical shift, the range of f is not going to change. The lowest this function gets is as close to 0 as you want, but never getting there. But the highest it gets knows no bounds. So the range of f is still 0 to infinity. Finally, for number 1, it's going to be a similar story to what we just saw in number 2. So the horizontal asymptote, since there was no vertical shift, we're still in the situation of having y equals 0. The domain of f, again, everything. And finally, the range of f, because there was no vertical shift, again, this will be 0 to infinity. So those are the 4 examples. On your exam, I'll usually put a couple problems you have to do. 1 or 2, we'll see, due to the whole COVID-19 situation. But you should be working on the homework and doing all of the graphing exercises. I mentioned at the beginning of the video, the compound interest type of problems. If you look at the handout, there's one more problem at the end of the handout. if I do get to it, I'll get to it during the application problem section, and we may go back to it. But as far as 4.1 is concerned, this is what I want you to focus on, what I've covered here. Okay, so hopefully that was clear. If you have questions, again, bring them to discussion, bring them to our quote unquote lecture sessions, and hopefully we'll be able to solve those questions for you. So I'll see you in class, and I will end here.